Hello students. Here we have to discuss the power flow diagram of three-phase induction motor, right? Since it is a motor, its input will be the electrical power input and the output will be the mechanical power output. Output will be mechanical and input will be electrical, right? So when you provide three-phase alternating current supply which is balanced in time on a balanced three-phase stator winding, then the power input will be P input, let me call it P input, it will be equal to root 3 times of line voltage VL into line current IL into operating power factor of the motor, that is cos phi, right? So in that case, this will be the electrical power input, that is root 3 VL IL cos phi. So in both the cases, the electrical power input would be root 3 VL IL cos phi. So if the winding is in star connection or if the winding is in delta connected, in both the cases the electrical power input will be root 3 VL IL cos phi. Winding may be connected in delta or it may be connected in a star, right? So if it is connected in delta, then three-phase power input will be 3 V phase into I phase into cos phi. So for delta connection, you know, I phase current will be equal to I line by root 3. So here root 3 get cancelled with 3, becomes root 3 VLIL cos phi, and had it been star connected and the winding being star connected, then you would calculate like P star, it will be 3 V phase I phase cos phi. It would be 3 for star connection, V phase will be equal to V line divided by root 3, line voltage divided by root 3. So into IL into cos phi. So root 3 gets cancelled with 3, becomes root 3 VLIL cos phi. So in both the cases, whether the winding is connected in delta or in star, in both the cases the power input would be root 3 V line I line cos phi. So from this power input, when you subtract the stator core loss and stator copper loss, you will get the power in air gap. You will get power in this air gap between stator and rotor, right? So the outermost frame is known as a stator, right? It is stationary, does not rotate, right? But the smaller circle, this smaller circle, this is basically rotor. It's a rotating element. It rotates in air gap, right? So here, when you subtract the stator core loss and stator copper loss from the input electrical power, then you will get power, air gap power in this air gap, right? So this air gap power is nothing but power input to this rotor. Air gap power is nothing but the power input to the rotor. So suffix G stands for gap. Gap means air gap. So this is power input to the rotor. So from this air gap power, when you subtract rotor core loss and rotor copper loss, you will get mechanical power developed. Mechanical power developed, right? Now from this mechanical power developed, when you will subtract the frictional and windage losses, then you will get the final output power at the shaft, that is final mechanical power output at the shaft. That is basically the useful power output, useful mechanical power output at the shaft that you can utilize, right? So this is the power flow diagram of three-phase induction motor. So here P input, that is electrical power input. From this, when we subtract stator core loss and stator copper loss, so P input, that is electrical power input minus stator core loss minus stator copper loss, will give you the air gap power PG. Now from this air gap power PG, when you will subtract the rotor core loss and when you will subtract the rotor copper loss, it will give you the mechanical power developed. Now in the running condition, the slip of the three-phase induction motor is low. It is around 4%, right? So if the slip is 4%, then for 50 Hz supply frequency, right, For 50 Hz supply frequency for 4% slip, the rotor frequency is 0.04 into 50, because you know that the rotor frequency is slip times of applied frequency to stator, right? So that is 0.04 into 50 becomes 2 Hz. That is very small value. And if the operating slip is 2%, then the rotor frequency will be equal to 0.02 into 50 Hz, that is 1 Hz, right? So that means in the running conditions, since the slip is low, so the rotor frequency is low, so that's why the rotor copper loss is very less, almost negligible. So we can neglect this rotor copper loss in the running condition. So PG minus rotor copper loss becomes PMD, that is mechanical power developed PMD. So PG minus the rotor copper loss, that is slip times of air gap power, right, that we have derived in the earlier expression. You can watch my earlier videos, right? So I have discussed that rotor copper loss, that is PCU, it is slip times of air gap power. So PG minus rotor copper loss, that is slip times of PG, air gap power PG. So rotor copper loss is slip times of air gap power PG, that will be equal to PMD. PG minus slip times of PG will be PMD, mechanical power developed PMD. Take PG common, PG bracket 1 minus S becomes mechanical power developed PMD. Now when you subtract frictional and windage losses, as you know that when the rotor will rotate, it will produce a frictional losses and windage losses, right? It will cut the wind around, right, in the air gap. It will produce the frictional and windage losses, that's why, right? So PMD minus friction windage loss will give you the output power at the shaft, that is final output power at the shaft. That is basically, you can write PMD, that is mechanical power developed, minus friction and windage loss. When you minus friction and windage loss from mechanical power developed, you will get the PSH, that is the shaft power output, or the final mechanical power output that you can utilize. So from these expressions, you can in short write the expression, the formula, that is PG raised to PCU, that is rotor copper loss, raised to PMD, that is mechanical power developed. PG is the air gap power, is equal to 1 raised to S, that is a slip, raised to 1 minus S, right? So PCU, rotor copper loss PCU, will be slip times of air gap power, and PMD by PCU will become 1 minus S by S, right? So air gap torque, you know, that is electromagnetic torque. It rotates at a synchronous speed. NS is given by 120 into supply frequency divided by number of poles. So omega S is the rotational speed in radian per second, right? That will be equal to 2 pi ns by 60, right? So air gap torque TE will be equal to air gap power divided by angular rotational speed in radian per second, omega S, right? So torque, air gap torque, is nothing but the air gap power per unit angular speed, right, per unit angular synchronous speed. So TE is equal to PG by omega S. Torque developed will be equal to TMD, mechanical torque developed, will be equal to PMD, mechanical power developed, divided by, here you will have to take rotor speed, right? Rotor speed, that is omega R. Omega R is equal to omega S 1 minus S, and PMD you have already calculated, that is PG into 1 minus S, right? So 1 minus S get cancelled, and from here you will get TE is equal to TMD, right? That is the air gap torque will be equal to mechanical torque developed. So that's how we can understand the power flow diagram of a 3-phase induction motor. So that's how the power flow from input to the output, right? So thank you very much. Thanks for watching. So subscribe to the channel. Please subscribe for all such kind of videos. Thank you very much.